Welcome to the next video in the threat hunting with open source software, Suricata and Elasticsearch. We're not quite to Suricata yet, but after the last video, we've made big strides in understanding how network data gets transmitted across the internet. We broke down a lot of the important layers in the OSI model, working up from the physical layer all the way up to layer 7, the application layer. In this video, we'll start capturing some live network traffic. I get to introduce you to Tcp Dump. We'll watch the output as we make some real live network requests, and we'll see how to capture network traffic that we've seen on the wire. Let's get ready to start digging in. Oh yeah, this video won't just be Google Slides. We'll see some actual video. We'll begin by diving into Tcp Dump by talking a little bit about our monitoring setup. Nothing in depth, but enough to know how we can monitor traffic. Then, it's all about the open source program, Tcp Dump. Tcp Dump is a simple to use command line utility that will grab packets from a network and output them for your consumption. Typically, you'll only be able to grab packets destined for the host on which you're running Tcp Dump, but if you use a piece of hardware called a hub or a switch with a mirror port, you can see traffic that's destined for elsewhere. For some use cases, you'll want to capture all the traffic on a network. If you want full visibility, capture all the things. If you're troubleshooting a specific application or host, then you'll want to apply a filter to what you're capturing. This is accomplished by using the Berkeley Packet Filter Language, or Bpf. Bpf allows you to specify attributes such as host, protocol, port, or VLAN, or if you want to get even more specific, you can actually look and filter based on the payload of the packets. It's easy to build a Bpf filter to grab something like only HTTP GET traffic. Monitoring a network is kind of tricky. Modern switches are super smart, and they only route traffic that's destined to a NIC to that switch port. For instance, if I have a 12-port switch, and I have a web server on the 3rd port, and my workstation makes an HTTP request to that web server, the switch will route that traffic to the web server port. It makes sense. It's efficient. Unfortunately, since that traffic doesn't go to the other ports on the switch, it's kind of hard to watch. Old school hubs that are still made, but only support really low rates of traffic, are much dumber. They send the network traffic to each port, since it's just a bunch of parallel electric circuits. No routing, no intelligence. So, how do we fix this in a modern network? There are a few options. A managed switch can frequently support what's called a mirror or span port. This tells the switch to mirror all the packets that the switch sees out the specified mirror port. Alternatively, we can use a network tap, which effectively does the same thing, but it's inline on a network cable. It has normal input and output ports to be invisible to the network, but it will also have one or more duplication ports, much like a mirror port on a switch. The last option, it's much more boring, but you can always run. The last option is much more boring, but you can always run tools like Tcp Dump or Suricata on a computer and only monitor traffic that's bound for it. In that case, you'd see broadcast traffic as well, since it's technically bound for every host in the network. Oh, right. You're probably wondering why I put the big bold word promiscuity up here. In order for a NIC to see network traffic, it has to pass from the network through the operating system to the user space. The NIC or the kernel will typically block traffic that is not destined for this machine. So, in order to tell the operating system and the NIC that we want all the traffic, we have to put the NIC in promiscuous mode. Otherwise, packets would be ignored somewhere up the data pipeline between Tcp Dump and the physical wire. Since we tell it to go into promiscuous mode, our application will see all of the packets that the NIC sees. And since we've set up the mirror port, it will be traffic that was not destined for this computer. Now I'll show you how I set it up in the switch that I have. This is the user interface for my cheapy little switch, it supports mirroring on any of the ports. What we'll do, we'll click on the forwarding tab, and here at the bottom we can say port mirroring. In this case, I know I have my network generator on port 4, so I'll uncheck port 3 because I don't want to mirror port 3 to port 5 where my monitoring application is. I do want the hardware that's plugged into port 4 mirrored out port 5. We check port 4, make sure it's mirroring out to port 5, hit apply, and we're done. Now we'll get into some video. I have my network set up with a mirror port on my switch that I showed you. My monitoring server has 2 NICs. One is set for regular network traffic, so I can SSH to it. The other is set for receiving the packets from the mirror port. Here, I'll look at the current NICs that I have. We can see that one has a network IP address and the other does not. We'll set the monitoring port into promiscuous mode, like we talked about. Now we'll run TCP dump using that interface. My first computer will issue an HTTP request to a website. How about www.fowie.com? Immediately, you'll see lots of packets streaming across the screen. The first computer is the only machine that's using the network port that's being mirrored. Since it's the only one being monitored, the packet should be pretty understandable. Let's do a little analysis. Here's the output of TCP dump. We can see timestamps, source IP addresses, destination IP addresses, protocols, even some layer 7 information. Now, let's say we want to write those packets to a file. We'll write them in raw PCAP format using TCP dump, so we can later analyze them in Wireshark Pro or even Suricata. Now let's think about another scenario. If we wanted to automate the capturing process for later analysis, we need to capture them to disk. So we need to figure out what packets to capture, how long to keep them for. We can target hosts, we can target protocols, we can target time ranges, but if we want to start capturing everything, you'll want to do a rotating disk, a rotating file system, or a set of data files like a DVR that you can hold for a specific amount of time or until your disk gets full. We can set up a round-robin storage so the newer data overwrites the older data. Alright, this video has been jam-packed. We went over TCP dump, the network setup with port mirroring, and how do we monitor the traffic. We've seen live network monitoring to the console as well as writing data to the disk. Now that we've written some packets to disk, we'll use Wireshark to analyze them in our next video.